What kind of engine is this that Japanese car manufacturers keep remembering, falling into a vicious cycle? When they have money, they research rotors. When they don't have money, they sell cars. That is the famous rotary engine. In this overview, we will explore the past and present of the rotary engine. Note that compared to traditional piston engines, the rotary engine has no pistons, no crankshaft, valves, or other standard parts. It has an eccentric shaft acting as the rotor carrier and a fixed gear to determine the rotor's rotation direction. The engine consists of a central housing, the rotor housing acting as the cylinder, and side housings. Rotary engines also have four strokes: intake, compression, combustion, and exhaust. During intake, the rotor turns and the chamber volume increases with rotation, creating a vacuum that pulls the air and fuel mixture into the chamber. As the rotor continues to turn, the intake closes and the volume decreases, compressing the mixture. Since the combustion chamber is long and narrow, two spark plugs often fire simultaneously. Additionally, the rotor has apex seals to separate the combustion chambers. Next, the ignited gas expands rapidly, pushing the rotor to create force, converting thermal energy into mechanical energy. Finally, during exhaust, the rotor opens the exhaust port, pushing gas out, completing a cycle. Compared to piston engines, every face of the rotor performs strokes simultaneously. One full rotor rotation performs work that makes the movement smoother. With only two moving parts, the structure is greatly simplified, compact, and has lower vibration. The chambers of the rotary engine are separated by several seals. The most important is the apex seal. For decades, this was a constant challenge for engineers. The development of the rotary engine began with a collaboration between Mazda and the German company NSU. At that time, NSU was quietly researching to launch the first car using a rotary engine, the NSU Spider, equipped with a single-rotor water-cooled engine. The next version was the RO80. At that time, it was extremely advanced, even equipped with a warning buzzer to remind the driver when the RPM neared 9,000 revolutions per minute. Although praised, the RO80 initially caused NSU to go bankrupt because the engine was not durable. The engine life was too short. Early cars could only go 50,000 kilometers before requiring an engine overhaul. The fatal flaw lay in the apex seals. To increase compression efficiency, the three rotor vertices must be airtight. This relies on the apex seals. What followed was a long optimization process. Initially, these seals were made of metal and pushed by springs to contact the housing wall. To reduce friction, they were often coated with a layer of oil. Because oil is continuously consumed during combustion, a separate metering pump was designed to supply oil. However, due to the direct contact of the apex seals, static friction and chatter marks, known as devil's claw marks, could cause serious scratches. Using lubricating oil alone could not completely avoid this. This placed higher demands on the seal material. Mazda initially used ceramic materials. Although effective, production costs were too high. The first real breakthrough was using cast iron. This design had two vertical holes and horizontal holes to dampen high frequencies. Later, to reduce production costs further, Mazda, in the 1967 to 1973 period, switched to using aluminum alloy seals. These seals used composite electroplating technology, SIP-Nicosil, with high hardness and self-lubricating properties, solving the friction problem with the rotor housing. From 1973 to 1975, seals utilized a new two-piece design, a main piece and a triangular corner piece. This significantly improved the sealing capability. The tip of the seal contacting the housing was also hardened using an electron beam crystallization method. Electron beam hardening is a material hardening technique utilizing energy from an electron beam. By shooting electron beams at the material surface, creating thermal heat, the temperature rises until the material hardness increases, giving the material superior wear resistance. By the early 1980s, the seals utilized a cutoff design extending the main body to increase sealing efficiency, aiming to reduce gas leakage at one end of the rotor tip. From 1985 to 2002, seal thickness was reduced to 2 millimeters. A new three-piece configuration replaced the previous two-piece design. Keeping the triangular corner part, the main piece was split horizontally and diagonally. The upper and lower parts could move vertically on the contact surface, further improving sealing capability. Additionally, Mazda injected lubrication into the center of the rotor tip for supplementary sealing. This version was used for the famous 13B engine, high-power, low-weight, turbocharged, which became the symbol of Mazda thanks to the third-generation RX-7. When the 13B ceased production, it was replaced by the Renesis engine, used in the RX-8. The seals of the Renesis engine had a two-piece design made from low-friction cast iron. The height of the seal was reduced to 4.5 millimeters, and the piece tips were rounded. Maximum RPM reached 9,000 revolutions per minute. However, the discontinuation of the Mazda RX-8 marked the end of the Renesis engine due to low fuel efficiency and emission issues. Despite facing many obstacles, Mazda continued to research this technology and turned it into a brand signature. 10 years later, at the 2021 Brussels Motor Show, they unveiled the newest version of the rotary engine, equipped on the MX-30. However, this is a hybrid car. The rotary engine is only used as a supplementary generator. Specific effectiveness still needs to be verified by the market. Hopefully, Mazda's efforts will be rewarded in the future.